The Improbable Ape, A Journey Through the Astronomical Odds of Human Existence, by Rob Corley. Written and produced by Rob Corley. The countdown that never reached zero continues to tick, but it no longer marks only the minutes until nuclear annihilation. Today, it measures something more insidious and perhaps more certain: the time remaining until we fundamentally break the planetary systems that made our existence possible. For 4.5 billion years, Earth has been a self-regulating system, maintaining conditions suitable for life through an intricate dance of atmosphere, oceans, ice, and living organisms. This system survived asteroid impacts, volcanic eruptions, ice ages, and mass extinctions. It created the stable climate that allowed agriculture to flourish and civilizations to rise. Now, for the first time in planetary history, a single species has become powerful enough to disrupt this ancient equilibrium. We have become a geological force comparable to volcanoes and glaciers, capable of altering the composition of the atmosphere, the chemistry of the oceans, and the very fabric of life itself. We have entered the Anthropocene, the age of humans, and we are unraveling the Eden that made us possible. This is not a story of inevitable doom, but of unprecedented responsibility. We are the first species to understand what we are doing to our planet, and potentially the first with the power to choose a different path. Whether we will exercise that power wisely may determine not just our own future, but the future of complex life on Earth. The Great Acceleration. The transformation began quietly, almost imperceptibly, with the first wisps of smoke rising from coal-fired steam engines in the 18th century Britain. The Industrial Revolution seemed like humanity's greatest triumph, the moment when we finally freed ourselves from the limitations of muscle power and began reshaping the world according to our desires. But something unprecedented was happening beneath the surface of this technological revolution. For the first time in Earth's history, a biological species was extracting and burning fossil fuels on a massive scale, releasing carbon that had been locked away for millions of years back into the atmosphere in a matter of decades. The scale of this transformation is difficult to comprehend. In the past 250 years, humans have burned through fossil fuel deposits that took 300 million years to form. We have released more carbon dioxide into the atmosphere than all the volcanoes on Earth have produced in the past million years. We have altered the chemical composition of the atmosphere more rapidly than any natural process, except perhaps the asteroid impact that killed the dinosaurs. Scientists call this period the Great Acceleration, the dramatic increase in human impact on Earth systems that began around 1950 and continues today. In just 7 decades, human activity has fundamentally altered virtually every aspect of the planet's functioning. The numbers tell a staggering story. Since 1950, the global population has tripled. Economic output has increased 12-fold. Energy consumption has increased 7-fold. Water use has increased 4-fold. Fertilizer consumption has increased 9-fold. We have produced more plastic than the total weight of all land animals. We have moved more earth and rock than all the world's rivers combined. But perhaps the most profound change is one we cannot see: the alteration of Earth's energy balance. By increasing the concentration of greenhouse gases in the atmosphere, we have trapped additional heat that would otherwise radiate back to space. The planet is now absorbing more energy than it releases, creating an energy imbalance that is driving changes throughout the Earth system. This energy imbalance is small in relative terms, less than 1% of the total energy Earth receives from the Sun, but in absolute terms, it represents an enormous amount of additional heat. Every second, Earth is absorbing the equivalent of 400,000 Hiroshima bombs worth of extra energy. This energy has to go somewhere, and it is driving changes in climate, weather patterns, ice sheets, and ocean circulation that will persist for centuries or millennia. The atmosphere transformed. The most visible sign of human impact on Earth systems is the transformation of the atmosphere. For the past 800,000 years, atmospheric carbon dioxide levels fluctuated between about 180 and 300 parts per million, driven by natural cycles of ice ages and warm periods. These fluctuations were gradual, taking thousands of years to unfold. In just 250 years, we have shattered this ancient pattern. Atmospheric carbon dioxide levels have risen from 280 parts per million before the Industrial Revolution to over 420 parts per million today, the highest level in over 3 million years. The rate of increase is unprecedented in the geological record, occurring roughly 100 times faster than the most rapid natural changes. But carbon dioxide is not the only greenhouse gas we have altered. Methane concentrations have more than doubled since pre-industrial times, driven by agriculture, fossil fuel extraction, and waste management. Nitrous oxide levels have increased by 20%, primarily from fertilizer use and fossil fuel combustion. We have also introduced entirely new greenhouse gases that do not exist in nature, including various industrial chemicals that can persist in the atmosphere for thousands of years. The cumulative effect of these changes is to trap additional heat in Earth's atmosphere, driving global warming at a rate that is unprecedented in human history. Global average temperatures have risen by about 1.1 degrees Celsius since pre-industrial times, with the warming accelerating in recent decades. This may seem like a small change, but it represents an enormous shift in the planet's energy balance. To put this in perspective, the difference between today's climate and the last ice age, when much of North America and Europe were covered by ice sheets, was only about 6 degrees Celsius. We have already achieved nearly 20% of that change in the opposite direction, and we are on track to reach or exceed ice age level changes within this century if current trends continue. The warming is not uniform across the planet. The Arctic is warming twice as fast as the global average, a phenomenon known as Arctic amplification. This is causing rapid melting of sea ice, glaciers, and permafrost, triggering feedback loops that accelerate the warming process. As white ice melts and is replaced by dark ocean water, more solar energy is absorbed rather than reflected back to space, causing further warming. The oceans in crisis. The oceans, which cover 71% of Earth's surface and contain 97% of its water, are bearing much of the burden of human-induced climate change. They have absorbed about 30% of the carbon dioxide we have released into the atmosphere, helping to slow the rate of atmospheric warming, but at enormous cost to marine ecosystems. When carbon dioxide dissolves in seawater, it forms carbonic acid, making the oceans more acidic. Ocean pH has already dropped by 0.1 units since pre-industrial times, representing a 26% increase in acidity. This may seem small, but pH is measured on a logarithmic scale, so small changes represent large shifts in ocean chemistry. Ocean acidification is sometimes called the other CO2 problem, and it poses a direct threat to marine life that builds shells and skeletons from calcium carbonate. As the oceans become more acidic, it becomes harder for corals, shellfish, and many microscopic marine organisms to build and maintain their calcium carbonate structures. This threatens the foundation of marine food webs and could lead to the collapse of entire ocean ecosystems. The oceans are also absorbing most of the excess heat trapped by greenhouse gases. More than 90% of the additional energy in Earth's climate system is going into the oceans, causing them to warm and expand. This thermal expansion, combined with melting ice from glaciers and ice sheets, is driving sea level rise that threatens coastal communities around the world. Ocean warming is also disrupting circulation patterns that have remained stable for thousands of years. The Gulf Stream, which brings warm water from the tropics to the North Atlantic and helps moderate Europe's climate, has weakened by about 15% since the mid-20th century. If this circulation system collapses, it could trigger rapid climate changes across the North Atlantic region. Perhaps most ominously, warming oceans are losing oxygen. As water temperatures rise, the ocean's ability to hold dissolved oxygen decreases. At the same time, warming enhances stratification, reducing the mixing that brings oxygen from the surface to deeper waters. The result is expanding dead zones, where oxygen levels are too low to support most marine life. The cryosphere collapses. Earth's ice, the cryosphere, is one of the most sensitive indicators of climate change, and it is disappearing at an accelerating rate. Arctic sea ice has declined by about 13% per decade since satellite observations began in 1979. The ice that remains is younger and thinner than in the past, making it more vulnerable to melting. The Greenland ice sheet, which contains enough water to raise global sea levels by about 7 meters, is losing mass at an accelerating rate. In the 1990s, Greenland was losing about 50 billion tons of ice per year. By the 2010s, this had increased to over 250 billion tons per year. The ice sheet is now losing mass faster than it can be replenished by snowfall. Even more concerning is the West Antarctic ice sheet, which is showing signs of irreversible collapse. Unlike the Greenland ice sheet, which sits on land above sea level, much of the West Antarctic ice sheet rests on bedrock that is below sea level. This makes it vulnerable to a process called marine ice sheet instability, where warming ocean water can undercut the ice from below, causing it to retreat rapidly. If the West Antarctic ice sheet were to collapse completely, it would raise global sea levels by about 3.3 meters. While this process would take centuries to complete, recent observations suggest that it may have already begun. Several major glaciers in West Antarctica are retreating rapidly, and computer models suggest that their retreat may be unstoppable. Mountain glaciers around the world are also retreating rapidly. The Himalayas, often called the third pole because they contain the largest concentration of ice outside the polar regions, are losing ice at an accelerating rate. This threatens water security for billions of people in Asia who depend on glacier-fed rivers for agriculture and drinking water. Permafrost, permanently frozen ground that covers about 24% of the Northern Hemisphere's land surface, is thawing at an unprecedented rate. This is releasing stored carbon in the form of carbon dioxide and methane, creating a positive feedback loop that accelerates warming. Permafrost contains about twice as much carbon as the entire atmosphere, so its thawing could significantly amplify climate change. The biosphere under siege. While climate change captures most of the attention, it is only one aspect of humanity's impact on the biosphere. We are also driving what biologists call the sixth mass extinction, a loss of biodiversity that rivals the great extinction events of the geological past. Species are disappearing at a rate that is 100 to 1,000 times faster than the natural background rate of extinction. We have already driven thousands of species to extinction, and millions more are threatened. Unlike previous mass extinctions, which were caused by asteroid impacts, volcanic eruptions, or other natural catastrophes, this extinction is being driven by a single species, us. The primary driver of biodiversity loss is habitat destruction. We have converted about 75% of the planet's ice-free land surface for human use, leaving little room for wild nature. Forests, grasslands, wetlands, and other natural habitats have been cleared for agriculture, urban development, and resource extraction. The remaining natural areas are often fragmented into small patches that cannot support viable populations of many species. Agriculture alone now covers about 40% of Earth's land surface, making it the largest human use of land. Modern industrial agriculture relies heavily on monocultures, vast fields planted with a single crop, that provide little habitat for wildlife. The use of pesticides and fertilizers further degrades the environment for non-target species. Overfishing has depleted marine ecosystems around the world. About 90% of large predatory fish have been removed from the oceans since 1950. Many fish populations have collapsed, and entire marine ecosystems have been fundamentally altered by the removal of key species. Pollution is another major driver of biodiversity loss. Plastic pollution has contaminated every corner of the planet, from the deepest ocean trenches to the highest mountains. Microplastics have been found in the food webs of virtually every ecosystem on Earth. Chemical pollution from pesticides, industrial chemicals, and pharmaceuticals is affecting wildlife reproduction, behavior, and survival. Climate change is now emerging as an additional threat to biodiversity. As temperatures rise and weather patterns shift, many species are struggling to adapt. Coral reefs, which support about 25% of all marine species, are experiencing mass bleaching events as ocean temperatures rise. Many species are shifting their ranges toward the poles or to higher elevations, but not all can move fast enough to keep pace with changing conditions. The nitrogen revolution. One of the most profound but least visible ways humans have altered Earth systems is through the transformation of the nitrogen cycle. Nitrogen is essential for all life. It is a key component of proteins and DNA. But most organisms cannot use the nitrogen gas that makes up 78% of the atmosphere. They depend on fixed nitrogen that has been converted into forms they can use. For most of Earth's history, nitrogen fixation was carried out primarily by bacteria, either living freely in soil and water or in symbiotic relationships with plants like legumes. This natural process limited the amount of fixed nitrogen available to ecosystems, making nitrogen a limiting factor for plant growth in many environments. In the early 20th century, German chemists Fritz Haber and Carl Bosch developed a process for artificially fixing nitrogen by combining nitrogen gas with hydrogen under high temperature and pressure to produce ammonia. This innovation, known as the Haber-Bosch process, enabled the mass production of nitrogen fertilizers that revolutionized agriculture. The impact has been staggering. Humans now fix more nitrogen than all natural processes combined. We produce over 100 million tons of nitrogen fertilizer annually, enabling the intensive agriculture that feeds much of the world's population. Without synthetic nitrogen fertilizers, it would be impossible to feed the current global population. But this nitrogen revolution has come with enormous environmental costs. Much of the nitrogen applied to agricultural fields is not taken up by crops, but instead runs off into waterways, where it causes eutrophication, the excessive growth of algae and other aquatic plants. When these organisms die and decompose, they consume oxygen, creating dead zones where most marine life cannot survive. Nitrogen pollution has created over 400 dead zones in coastal waters around the world, covering an area larger than the United Kingdom. The Gulf of Mexico dead zone, fed by nitrogen runoff from the Mississippi River basin, can cover an area the size of New Jersey. These dead zones are expanding as agricultural intensification continues. Excess nitrogen also contributes to air pollution and climate change. Nitrogen oxides released from fertilizers and fossil fuel combustion contribute to smog formation and acid rain. Nitrous oxide, a byproduct of nitrogen fertilizer use, is a potent greenhouse gas that contributes to both climate change and ozone depletion. The phosphorus problem. Phosphorus presents a different but equally challenging problem. Unlike nitrogen, which is abundant in the atmosphere, phosphorus has no significant atmospheric reservoir. All the phosphorus available to life comes from the weathering of rocks, making it the ultimate limiting nutrient for life on Earth. Humans have dramatically accelerated the phosphorus cycle by mining phosphate rock and applying it to agricultural fields as fertilizer. We now move about 4 times as much phosphorus as all natural processes combined. This has enabled the agricultural productivity that supports the current global population, but it has also created serious environmental problems. Like nitrogen, excess phosphorus runs off from agricultural fields into waterways, where it contributes to eutrophication and dead zone formation. Phosphorus pollution is a major driver of harmful algal blooms that can produce toxins dangerous to humans and wildlife. But phosphorus also presents a resource scarcity problem. Unlike nitrogen, which can be fixed from the atmosphere, phosphorus must be mined from finite deposits of phosphate rock. These deposits are concentrated in just a few countries, with Morocco controlling about 70% of known reserves. At current rates of use, high-quality phosphate rock could be depleted within 50 to 100 years. This creates a paradox. We depend on phosphorus fertilizers to feed the global population, but our use of phosphorus is both environmentally destructive and ultimately unsustainable. Finding ways to recycle phosphorus and use it more efficiently is one of the great challenges of the 21st century. The urban planet. One of the most visible signs of the Anthropocene is the transformation of Earth's surface by urbanization. For the first time in human history, more than half the global population lives in cities, and this proportion is expected to reach 68% by 2050. Cities now cover only about 3% of Earth's land surface, but they consume about 78% of global energy and produce about 70% of carbon emissions. The growth of megacities, urban areas with more than 10 million inhabitants, is particularly striking. In 1950, there were only 2 megacities, New York and Tokyo. Today, there are over 30, and the number is expected to reach 43 by 2030. Some of these urban agglomerations, like the Pearl River Delta in China, now house over 100 million people. Urbanization has profound effects on local and regional environments. Cities create heat islands that can be several degrees warmer than surrounding rural areas due to the absorption of solar energy by concrete and asphalt. They alter local weather patterns, often increasing precipitation downwind of urban areas. They fragment natural habitats and create barriers to wildlife movement. Cities also concentrate pollution and waste. Urban air pollution kills millions of people annually and contributes to climate change. Urban waste streams, including sewage, solid waste, and industrial effluents, can overwhelm local ecosystems if not properly managed. Many cities in developing countries lack adequate waste treatment infrastructure, leading to widespread pollution of air, water, and soil. But cities also offer opportunities for more sustainable living. Urban residents typically have smaller carbon footprints than rural residents due to more efficient transportation, housing, and energy systems. Cities can be centers of innovation for clean technologies and sustainable practices. The challenge is to harness the benefits of urbanization while minimizing its environmental impacts. The plastic planet. Perhaps no single material better symbolizes the Anthropocene than plastic. Since mass production began in the 1950s, humans have produced over 9 billion tons of plastic, more than the weight of all land animals on Earth. About 6.3 billion tons of this plastic has become waste, and only about 9% has been recycled. Plastic pollution has contaminated every environment on Earth. Microplastics, tiny fragments less than 5 millimeters in size, have been found in the deepest ocean trenches, on the highest mountains, in Arctic ice, and in the food webs of virtually every ecosystem. They have been detected in drinking water, food, and even human blood and placental tissue. The environmental impacts of plastic pollution are still being discovered, but they are clearly significant. Marine animals mistake plastic debris for food, leading to malnutrition and death. Microplastics can carry toxic chemicals and pathogens, potentially affecting the health of organisms throughout food webs. Plastic production and disposal also contribute to climate change through greenhouse gas emissions. The scale of plastic pollution is staggering. Every minute, the equivalent of a garbage truck full of plastic enters the oceans. At current rates, there could be more plastic than fish in the oceans by 2050. The Great Pacific Garbage Patch, a concentration of plastic debris in the North Pacific, is now larger than twice the size of Texas. Addressing plastic pollution requires fundamental changes in how we produce, use, and dispose of materials. This includes developing biodegradable alternatives, improving recycling systems, and reducing single-use plastic consumption. Some countries and cities have begun banning single-use plastics, but global action is needed to address this planetary-scale problem. The tipping points. One of the most concerning aspects of human impact on Earth systems is the potential for triggering irreversible changes known as tipping points. These are thresholds beyond which a system shifts into a fundamentally different state, often with little possibility of return. Climate scientists have identified several potential tipping points in the Earth system. The collapse of the West Antarctic ice sheet mentioned earlier is one example. Others include the shutdown of the Atlantic circulation system, the dieback of the Amazon rainforest, the release of methane from thawing permafrost, and the loss of Arctic sea ice. What makes tipping points particularly dangerous is that they can interact with each other, creating cascading effects that accelerate change throughout the Earth system. For example, the loss of Arctic sea ice reduces the planet's ability to reflect solar energy, causing more warming. This warming accelerates permafrost thaw, releasing more greenhouse gases, which causes more warming. The warming also increases the risk of Amazon dieback, which would release even more carbon. Some scientists warn that we may be approaching a hothouse Earth scenario, where cascading tipping points lock the planet into a much warmer state, regardless of human actions. In this scenario, even if we stopped all greenhouse gas emissions tomorrow, the Earth system would continue warming due to self-reinforcing feedbacks. The exact locations of these tipping points are uncertain, but there is growing evidence that some may be closer than previously thought. The Amazon rainforest, for example, is showing signs of stress from drought, deforestation, and warming temperatures. Some parts of the Amazon are already releasing more carbon than they absorb, transforming from a carbon sink into a carbon source. The Anthropocene paradox. The emergence of the Anthropocene presents humanity with a fundamental paradox. The same technologies and systems that have enabled unprecedented prosperity and population growth are now threatening the stability of the Earth system that supports us. We have become so successful as a species that our success is undermining the conditions that made it possible. This paradox is evident in many aspects of modern life. The fossil fuels that powered the Industrial Revolution and lifted billions out of poverty are now driving climate change that threatens global stability. The agricultural systems that feed the world's population are degrading the soils and ecosystems they depend on. The economic growth that has created unprecedented wealth is consuming resources faster than they can be replenished. The Anthropocene also reveals the interconnectedness of human and natural systems. We can no longer think of nature as something separate from human society. Human activities now influence every aspect of the Earth system, from the composition of the atmosphere to the chemistry of the oceans, to the distribution of species across the planet. This interconnectedness means that environmental problems are also social, economic, and political problems. Climate change is not just a technical challenge that can be solved with better technology. It is a collective action problem that requires unprecedented cooperation among nations, communities, and individuals. Biodiversity loss is not just an ecological issue. It threatens food security, human health, and economic stability. The Great Turning. Despite the scale and urgency of the challenges we face, there are reasons for hope. Around the world, people are beginning to recognize the need for fundamental changes in how we relate to the natural world. This recognition is driving what some call the Great Turning, a shift from an industrial growth society to a life-sustaining civilization. This transformation is already underway in many sectors. Renewable energy is now the cheapest source of electricity in most parts of the world, and its deployment is accelerating rapidly. Electric vehicles are becoming mainstream, with many countries planning to phase out internal combustion engines. Sustainable agriculture practices are spreading as farmers recognize the need to protect soil health and biodiversity. Cities are implementing innovative solutions to reduce their environmental impacts. Green buildings, urban forests, renewable energy systems, and circular economy approaches are becoming more common. Some cities have committed to becoming carbon neutral or even carbon negative within the next few decades. The financial sector is also beginning to recognize climate and environmental risks. Investors are increasingly divesting from fossil fuels and investing in clean technologies. Central banks are incorporating climate risks into their assessments of financial stability. Insurance companies are adjusting their policies to reflect the growing risks from extreme weather events. Perhaps most importantly, there is growing recognition that addressing environmental challenges requires not just technological solutions, but also changes in values, behaviors, and social systems. This includes shifting from a focus on endless economic growth to measures of well-being and sustainability. It includes recognizing the rights of nature and future generations. It includes developing more equitable and just societies that can respond effectively to global challenges. The choice before us. The Anthropocene is not just a description of what has happened. It is a call to action about what happens next. For the first time in Earth's history, a single species has the power to consciously direct the evolution of the planet. This power comes with enormous responsibility. We face a choice that will define the future of human civilization and the fate of countless other species. We can continue on our current path, treating the Earth as an inexhaustible source of resources and an infinite sink for waste, until we trigger irreversible changes that undermine the foundations of complex life. Or, we can choose to become responsible stewards of the planet, using our knowledge and technology to create a sustainable and just future for all life on Earth. This choice is not just about technology or policy, it is about who we choose to be as a species. The same cognitive abilities that created the Anthropocene crisis also give us the power to solve it. Our capacity for imagination, cooperation, and innovation, the traits that made us the improbable ape, are exactly what we need to navigate the challenges ahead. The countdown that never reached zero continues to tick, but now it measures something different. It measures the time we have left to choose our future, to decide whether we will be remembered as the species that destroyed the Eden that made us possible, or as the species that learned to live within the boundaries of the only planet we have. The clock is still ticking, the choice is still ours, and the time to choose is now.